Hello physics students. So today you're going to learn about something called the Doppler effect, or sometimes called the Doppler shift. Now, the Doppler effect can happen with any kind of wave. What you need for it to happen is first a source of a wave and an observer. So in the case of light, maybe you have one person over here shining a light, and then another person over here observing that light or receiving that light. Or maybe in the case of sound, you have one person here holding a speaker playing music and another person over here listening to the music. So for both these waves, the Doppler shift can occur, and what it is the Doppler shift is the change in frequency of an absorbed wave caused by motion. That's the key, of either the observer and or the source of the wave. So before I go into more notes of why it happens and how much it happens, first I want to show you a clip of the Doppler shift happening. What you should have observed was that the pitch of the train horn changed. It was higher as the train approached, and then as the train passed, it got lower. Now, what do I mean by the pitch? The pitch is related to the frequency, but how you detect it is through your hearing. You would hear, like say for a normal train horn, maybe it's honk, and then as the train is approaching, it's higher. So instead of honk, it's honk. You hear that higher pitch. And then as the train passes, instead of honk, honk, honk. So you hear that lower tone as it passed. That's what I mean by the frequency changing, the pitch changing. Now, to be fair, the loudness also changed. The train got louder also as it approached, simply because when you're closer to a speaker, you hear the speaker louder. And then the train volume went down or the loudness as the train passed, simply because the train's getting further away. But that's not the Doppler effect. The Doppler effect is the change in the pitch, the tone. In other words, honk, honk, honk. That is the Doppler effect. So again, I'll play the same clip again and watch for that change in tone and note it. Okay, so in that clip, you saw the train, which had the horn. In other words, the source was moving toward the observer and the observer was at rest. They were standing on the ground. So source moves, observer at rest, Doppler shift. In the next clip, you're going to see that the same effect happens when the source this time is the one at rest and the observer's moving. So this time there's a car parked on the side of the road, and then there's another car driving, and the car parked is holding down the horn honking, and then the observer drives by that. So watch and see that change in pitch. So again, it's the change in pitch that's the Doppler effect. Yes, the car horn got louder when the person was approaching and then quieter when the person drove past that car. But again, the Doppler effect is the tone changing, the pitch changing, the frequency changing that the observer hears. In other words, a normal car horn is honk, and then as the car was approaching, we heard not honk, honk, but honk, and then honk. So I'm exaggerating, but that's the Doppler shift, how the pitch went up and then down. But the key note here is that as the car was coming toward the horn, the pitch went higher, and then as it passed, the pitch went lower. So let me just show you that clip again quickly so you really note that effect occurring. So now I want to explain why that happens. So first of all, remember that when a speaker is making sound, what it's doing is lunging forward and repeatedly creating compression after compression, which then race through space to an observer, like maybe me. So suppose there's a speaker over there and it's sending out, and each of these little tape marks represent the compressions of a wave with a wavelength of 10 centimeters. Now, as these go past me at 331 meters per second at STP, or maybe in this room more likely like 340 meters a second. So this races by and covers 3+ football fields in 1 second. So it goes extremely fast. But as it goes by my eardrum, the compressions strike my ear at a certain rhythm, like this. So they make my eardrum vibrate, and then I perceive that as a particular tone. The faster my eardrum vibrates, the higher the tone sounds. It gets more into the honk, that squeaky level. The less frequent that my eardrum gets struck, the lower the sound is, like honk, like that. So why would moving toward the source create a higher frequency? Well, imagine as these are going by, I start walking in this direction. Well, isn't that going to make me strike and reach the next compression instead of waiting for it to get to my ear? I'm going to also, as it's moving forward, I'm going to move forward. I'm going to get there quicker, which means that if there's less time between compressions, that means more of them will hit my ear in 1 second, and that means the frequency is higher. So as I'm going toward the source, I register a higher tone. And you could also imagine it's a little harder to do, but as these are going by and then as I start walking away, then it'll take longer, because as the next compression is coming, I'm also moving away from it. So that means that there'll be more time to the next compression, which means not as many of them will hit my ear per second, meaning the frequency will be lower. So towards the source, higher frequency; away from the source, lower frequency. So let's diagram that and summarize. So case one, the observer moves. We got a speaker here oscillating, creating compression after compression that makes sound a longitudinal wave, because the vibrations of the molecules are this way as the wave is moving this way. So the vibrations and the motion are parallel to each other. So as we learned in the sound video, longitudinal wave. So as these compressions come toward me, I can either move towards the speaker, the source, or I can move away from the speaker. If I move toward, as I just explained, I'm going to get more compressions in my ear per second, so that causes the observer to hear a higher frequency pitch, not louder, but it makes the sound more like a squeak. When I move away, then what happens is that causes the observer, me, to hear a lower frequency. The pitch is lower. That means it doesn't mean that it's quieter. It means that it sounds more like a bass guitar. So let me create a pause to allow you to copy these notes down. Okay, so the next thing that I want to do is talk about, well, okay, that's when the observer moves. Why did the Doppler shift happen when the source moved, like in the first set of video clips with the train? But before I do that, I want to just show you several more clips, just so you could really see the Doppler effect happening for a whole bunch of situations: sirens, trains, car horns. So let me start those videos so you could observe more Doppler effect happening. hopefully you noted that in all cases when the source was approaching, the sound was higher, the tone was higher, the frequency was higher. And in all cases when the source started going away from the observer, the frequency went down. So why does that happen? Well, to answer that question, I'm going to ask you to imagine, forget about right now sounds or even light. Imagine that you take like a moth, and maybe the moth falls into a pond that's perfectly still, and it's trying to get out of the water, so it's flapping its wings like this. Well, just like when you drop a stone into a pond, it makes like a ring that spreads out. If the moth keeps tapping its wings, it'll send ring after ring out. And if the moth isn't moving, then what happens is these rings are all concentric. Every time it taps, it makes a new a wave, and then it taps again, a new wave. So you've got more and more waves coming from this central point. Now, the moth is not moving, so all the waves remain concentric. And if there were two other bugs, A and B, sitting here, eventually these waves would reach those insects and they would start bobbing up and down, like imagine you on an inner tube in the ocean bobbing up and down. So that those two would bob up and down at the same frequency that the source, this moth, is tapping its wings, because there's basically no difference in caused by the motion. Nothing is moving here. Now imagine that that same moth, while trying to fly away and flapping its wings like this, starts kicking its legs and starts swimming towards shore. What happens is the very first time it tapped its wings, it was somewhere over here maybe. And so this is the wave caused by the first wing tap spread out circularly from this point where the bug was at this instant. But the next time it taps its wings, it's not at this spot, in the same spot. It has moved, because it's swimming, to somewhere around here. So this second wave here started from here. So this is the center of this circular wave. The third time it taps its wings, it's moved again. So this third wave was started here because of the motion. And so it spreads out like a circle from that point. And what you see is, because of the motion, each wave gets displaced, each circular wave gets displaced a little bit to the right in the direction of the motion. And what the result of that is that the waves pile up here and get closer and closer together, and they spread out back here and get further and further apart. And so what happens is, with the waves having the same speed, V equals lambda times frequency, if the wavelength got smaller over here, as we could see, the frequency went up. So the swimming bug is tapping like this, and the bug in front that's getting approached by the swimming bug, instead of going up and down like this with the frequency of the wing taps, it goes up and down like this at a higher frequency. And that means the frequency observed for A higher, because the source is moving toward him. Whereas observer B over here, I put the label over here. Maybe I should put it closer. Doesn't look so clear. So let's put B right here. Observer B, because the wavelengths are more spread out, for the same wave speed, the frequency is now lower. So instead of going up and down at the same frequency that the bug is tapping its wings, observer B, instead of going up and down like this, is going up and down at a slower frequency. So B observes a lower frequency because the source is moving away from him. So that's the reason why the waves pile up here, spread out back here. So take a moment to copy this down. Okay, so that's the reason, the ideas, the concepts. You need to make sure these are kept straight in your mind. When does the frequency go up? When does it go down? The concepts behind that, I'll summarize later, but just so you know, that's really important on the Regents. What I want to do now is move on to the equation that tells us exactly how much this shift occurs. So Let me make some room and I'll write the equation here. Okay, so the frequency observed is equal to the original frequency of the source. This here is the speed of sound under those conditions, or I should say speed of the wave, because it doesn't need to be sound. Speed of, and that's in the numerator and the denominator. This is the speed of the observer. This is the speed of the source. So go ahead and copy that equation down now. All right, so what I want to do is now an example. So maybe I'll write the example down here. Okay, so we've got a robber speeding away from a cop at 40 meters a second. The cop is chasing at 50 with a siren of 200 hertz. What frequency does the robber hear? So you see the cop, you got both moving, the source and the observer, and so the cop is moving faster than the robber. What frequency does the robber observe? So what we're going to do is use this equation. So I'm going to erase this to make room, because what I want to do is leave these notes undisturbed. So the first case, we got to start with the equation, and I'm going to shorten it a little bit. I'll put OB's S for observe, F source. Okay, so I forgot to say that this is at STP, standard temperature and pressure. So where can I squeeze this in? Maybe I'll just do something like this, STP. Okay, so we wrote out our equation as we're supposed to on the Regents. O equals, why did I put equals? That's times. Okay, so now what I'm going to do is plug in my data. Now, I left the plus or minus out because here's the challenging part. What you have to do is you have to decide. You can't just plug in and expect to get the answer like mindlessly. You have to decide whether you're going to put a plus or a minus here. And you decide based on your understanding of the concept of the Doppler effect. So the 40 meters per second, it's away from the source. So you have to think in your mind, when the observer races away from the speaker, does that make the frequency go up or does it go down? In class, I would stop and ask for people to raise their hand. You think it should be up or down? But of course, I can't do that now, but maybe I'll create a pause to allow you to decide this. So think in your mind, should the robber's velocity cause an increase or decrease in the observed frequency? You should have said it makes the frequency go down when you're racing away from the source. Now, the next question. So in order for this velocity to make the answer get smaller, in the numerator, do I have to put in a plus or do I have to put in a minus? So I'll create a pause, think about it, and decide in your mind. You should have said a minus sign. And that will make the overall answer smaller when you make the numerator smaller. The next question, do we put a plus or a minus here? So we have to go back to our understanding of the Doppler shift. We have to think about when the source is approaching the observer. Think about the trains that you watched or the car horns. Does that make the frequency go up or does it make it go down? So I'll create a pause for you to decide that. Hopefully you said when the cop is coming toward the observer, that's going to make the frequency go up. So now the next question is, do we put in a plus or a minus here? If we want our answer to get bigger over here in the denominator, do we put a plus or minus? So I'll create a pause, think about it, and decide. Hopefully you said, I'm going to put in a minus. You want a bigger answer? You need a smaller denominator. How do you make a smaller denominator? You subtract that off. And now once you do, see, it's hard. You got to do a lot of thinking there. 4 kinds of questions you have to answer. Punch this all on your calculator very carefully. And I believe the answer is 207 hertz. A little bit higher than the original. All right, so I'm going to create a pause, but remember this is out of order. So this copy first, and then the solution second. So go ahead and do that now. All right, so the reason why I scrunched everything here, because I wanted to leave this stuff up, because I want to just tell you, on the Regents, the more important thing than using the formula, which hardly ever comes up, are just the concepts of when or what kind of shift occurs for what kind of motion. So what you need to know is that when down pat, you should know this cold, that when the observer comes toward the speaker, the frequency goes up. When the observer moves away from the speaker, the frequency goes down. The next concept you need to know is that when the source comes toward the observer, frequency goes up. When the source moves away from the observer, frequency goes down. Those 4 ideas are the most important thing in this video about Doppler shifts, so make sure you know that. Now, the last thing that I want to do is just talk about some of the applications of the Doppler shift. What it's most commonly used for is actually determining these velocities. So, like for example, you know police officers give speeding tickets. They have a radar gun. They could shoot at your car. Actually, I think they're now mounted right on the car. And the radar gun somehow knows how fast you're going without seeing your speedometer. How does it do that? The radar gun sends out not sound waves, but electromagnetic waves. And Doppler shift occurs with all waves, even electromagnetic waves. So it's sending out radar waves crest after crest at your car. If your car is not moving, the crests hit your car and bounce off and come back to the police officer's radar gun at the same frequency. But if your car is moving away, then what happens is as the crests strike your car's moving away, so they come back with a longer wavelength and a lower frequency. If your car is coming toward, it's going to crash into the crests more rapidly and send them back at a higher frequency to the police officer. So the radar gun, it knows what frequency it's sending out because it's manufactured. It measures, in a sense, what comes back. It knows the approximate speed of sound for that day. It knows the police officer's speed. And the software can solve for this. And then it can give the police officer back a number. Hey, this person's going this speed. Are they speeding or are they not? And that's how the radar gun works. A similar manner, Doppler radar for weather. It sends waves at clouds, and if the clouds are moving towards or away from the radar, it can measure the speed, and then we can detect or predict when the storm will arrive based on whether it's coming toward us, what speed, so on and so forth. And the last application I want to mention is something very interesting. Physicists know that our universe is expanding. And you may be wondering, how do you know that the universe is expanding? We're stuck on Earth. How do we know that all those galaxies all the way across the universe are getting further from us? What astronomers have done, the first person to do this was a man named William Hubble, and he looked at stars and he noticed that the frequency of the starlight was shifted. And so he determined, or he concluded, that the stars were all moving away from us. The galaxies far away were moving away from us. And so in this image I'm showing you right now, you can see several what we call spectrums of the stars. In the middle image, you could see that there are some black bands missing light in an otherwise full spectrum of light coming from stars. The reason why those are there are beyond this video. We don't need to get into that. We'll get into that later in the year. But if the star is moving away from us, what happens is the frequencies of the starlight received get shifted lower. And what's at the lower end of visible light is red. So they call it red shift because all these bands move slightly toward the red. They don't become red. It's just that they move a little bit to the red. And that then tells us the stars are moving away from us. And we could also tell by exactly how much these shift, how fast they're moving. And so Hubble noticed that basically galaxies further from us move away from us even faster than galaxies close to us. And so he was able to conclude that the universe is expanding. Imagine like pulling a rubber band and all the points, if you put dots on the rubber band with ink, then as you stretch the rubber band, all the points are moving away from each other. So that's how he was amazingly able to conclude the universe was expanding. If the stars were moving toward us, that would shift the frequency of observed starlight up to a higher frequency. What's at the higher range? Blue light. So if we saw blue shift, doesn't mean the stars will look blue. All the frequencies just shift a little bit more to the blue. Then we would know the stars are moving toward us. But that's not what happened. They were moving away. So we were able to conclude, or physicists, that the universe was expanding. All right, so that's the Doppler shift. So basically, again, these concepts, the 4 ideas are important. Go back, look at your notes, quiz yourself, blindfold yourself, and see that you could tell, okay, if the source is moving away, if it's moving toward, if the observer is moving away, moving toward, all 4 of those situations, what happens to the frequency? Look a little bit about the calculation, and also know that the application, it's often used to determine the velocity of something moving, whether it's you on the highway with a cop radar gun, clouds in the sky with the Doppler shift radar, or starlight. You could detect motion in things from this shift, the Doppler shift. All right, so I hope you enjoyed the video. I hope you enjoyed all the little video clips of the Doppler shift. I'll see you in the next physics video.